All right, y'all. So today we're going to look at a little applied introduction to some statistical tests, t-tests, which I'm sure you're familiar with from your introductory stats course, and correlation, which you might be familiar with from your introductory stats course, and OLS, which you also might be. I don't really know what they teach in 101, but we're going to go over this. I know that Dr. Peterson has talked about OLS at least in the main course, the main 301 course. So, but yeah. So we're just going to kind of go through the code for it here. So we start by importing the tidyverse because we are typically going to be doing that. Then I set up the data frame like I've done a couple times and stuff like this where I just make data using the normal distribution. Just makes it really nice and clean for us just so I don't have to mess with regular old data that isn't as nice and maybe might be confusing. So these are just some variables. Why isn't it letting me? Okay, that works. So then we're going to use the COR function, which calculates the correlation matrix for us. So it gives us the correlation between, again, in a matrix format down here, x1 is perfectly correlated with x1, right? And that makes sense. I think you've talked about correlation in 301, but it's the degree that an increase in one is correlated with an increase in the other. It's the Pearson's R squared value, and you can look that up. Though I'm pretty sure Dr. Peterson has talked about it. So it gives us a nice correlation between the two variables. And now we're going to plot it, and you can see we plotted here, but I'm just going to show you how it runs in R. So we run that, and it gives us it's pretty clear here what the relationship is. But it's good to kind of, go through with rigor, and then I'll kind of go through this next line of code. Let's move you down there. This next little chunk. So we use geom jitter up here just because, you could use just use geom point. In fact, we probably should. That's fine. So here we do the same thing. We do geom point, position is jitter. You can add the jitter, add an alpha. Alpha is just, you can change that, and it just makes, that's spoilers, but that just makes the dots faded. You can make it all the way down to 0.1. You can barely see them, or you can just make it 1 so that they're obvious. I don't know why I specified. I think it was at 0.8 before. I don't know, it just kind of makes the line more clear. Kind of just, I don't know. Maybe I was just doing that to show what that did before. But yeah, so that just plots it the same as before. And then we add this geom smooth, as you can see here. We specify where the data is coming from, just like we did in the original. So data equals data, because we save the data frame object as data. So if we put data, that's what we're doing up here. And we specify it down here. Put method. I specified the color, and then I said standard error is off. If you set that to true, you get the standard error bars, or the standard error little shade around it. We don't need that here. It's nice to have sometimes, but yeah. So specify the color. So just by specifying the linear model, it automatically uses the formula y as a function of x. And because we specified x2 as the y and x1 as the x, it's looking at x2 as a function of x1, and it's plotting that ordinary least squares line, and we talked about that, or you all talked about that in 301, where it's minimizing the sum of squares of the residuals. So the residual is the amount of difference between the line and particular points. If we zoom in, so it's the difference between the dot and the line of best fit, which minimizes the sum of the squared values of these residuals when we square those values to punish outliers more so that it's fitting the data more nicely. So then, and I've got the code written out here. doesn't like that. Wait, I gotta copy and paste it. Okay. Yeah, so we do this, we can do that here with ggplot, and that's how we plot it. But if we just wanted the regression diagnostics, we would use the LM function. If we look at the LM function, yeah, fitting linear models, we can fit linear models using this. And so we specify the data as data. NA action, we're just excluding NA values. That's if you have non-available observations in your data. I don't know why I put that there, because I made the data so I know there's no missing values. That's fine. So we have x2, which remember is what our y was up here. We have x2 as a function of x1. And so we save that to an object. It gives us a list object that has all of the regression stuff. And we can use the summary, and we can look at the regression output, and it gives us some information about the residuals, some summary statistics about the residuals, and it gives us the coefficients, the coefficient of the intercept, p-value, t-statistic. It looks like this is statistically significant, which makes sense because I only differed the standard deviation by a little bit. So it's pretty positively correlated, as we saw before, so it makes sense that this line fits pretty well. Yeah. And so I didn't put this in this one, but we can also do a t-test, and I've mentioned this before. So we do data x1 and data x2. We can just look at a Welch's two-sample t-test for that. For the means of those two distributions. Yeah, so this is just a quick kind of overview on how this code works and what's going on. If you have any questions, let me know. And but yeah, we're gonna call that good.